everybody, how are you all? So, guys, today I've come up with something interesting, however easy. We've always heard about Schrodinger, haven't we? Most of us have. But do you actually know about his contribution to physics, especially quantum physics? If yes, great. If no, nothing to worry. I'm all here for you. So basically, our topic of discussion today is going to be the Schrodinger time independent and Schrodinger time dependent equations. However, I will start with a brief introduction of Schrodinger and his experiments. Erwin Schrodinger was an Austrian theoretical physicist and scholar who came up with a groundbreaking wave equation for electron movements. He was awarded the Nobel Prize in 1933 in physics. Erwin Schrödinger's most famous thought experiment, called hypothetical, became known as Schrödinger's cat. Although this experiment wasn't real and therefore did not scientifically prove anything, Schrödinger's cat was simply a teaching tool that Schrödinger used to illustrate how some people were misinterpreting quantum theory. In quantum mechanics, Schrödinger's cat illustrates a paradox of quantum superposition. In the thought experiment, a hypothetical cat may be considered both alive and dead simultaneously as a result of its fate being linked to random subatomic event that may or may not occur. In simple terms, Schrödinger stated that if you place a cat and something that could kill the cat, like a radioactive atom, in a box and sealed it, you would not know if the cat was dead or alive until you opened the box, so that until the box was opened, the cat was, in a sense, both dead and alive. This is all about Schrödinger's thought experiment, and we will now proceed to the main discovery made by Schrödinger, that is, the wave equations, that is, time-dependent equations and Schrödinger's time-independent equations. So as you can see, guys, here we have the derivations for time-independent Schrödinger equation. Let us first see what it states. The non-dissipation of the wave packet of the material particle has been explained by assuming the necessity of the guiding wave obeying Schrödinger wave equation, which we shall derive here. Consider a system of stationary waves to be associated with a particle. Let psi r, t be the wave displacement for the de Broglie wave at any location r equals to ix plus jy plus kx at time t. Then the differential equation of the wave motion in three-dimensional in accordance with Maxwell's wave equation can be written as del square psi equals to 1 upon u square curl square psi upon curl t square, or you can write this term as del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square equals to 1 upon u square curl square psi upon curl t square, where u equals to wave velocity. The solution of equation 1 gives psi as a periodic displacement in terms of time, that is, psi r, t equals to psi naught r e raised to power minus I omega t. You name this as equation 2 and name this as equation number 1. Where psi naught is the amplitude and the point considered. It is a function of position r, that is of coordinates x, y, z, and not of time t. The equation 2 may be expressed as psi r, t equals to psi naught r e raised to power minus I omega t. You can name this as equation number 3. Now, differentiating equation 3 twice with respect to t, we get. So when we differentiate this equation twice with respect to t, what are we going to obtain? Curl square psi upon curl t square equals to minus omega square psi r, t. Substituting this in equation 1, we get curl square psi upon curl x square plus curl square psi upon curl y square plus curl square psi upon curl z square equals to minus omega square upon u square psi. And you can name this as equation number 4. that angular velocity omega is given by 2 pi v. So you can write as, but v equals to u upon lambda. So you can write omega equals to 2 pi u upon lambda. That is, you take u on the other side, what you obtain? Omega upon u equals to 2 pi lambda, 2 pi over lambda. Also, curl square psi over curl x square plus curl square psi over curl y square plus curl square psi over curl z square equals to del square psi. We know this, and you can name this as equation number 6. Now using 5 and 6, equation 4 becomes del square psi plus 4 pi square upon lambda square psi equals to 0. Equation number 7. So far we have not introduced wave mechanical concept, and so the treatment is general. For introducing the concept of wave mechanics, we must put from de Broglie equation the value of lambda. What is the value of lambda according to de Broglie equation? That is h upon mv. You can name this as equation number 8. The next step is substituting this in equation 7 we get. Substituting the value of lambda in equation number 7, what do you obtain? Del square psi plus 4 pi square m square v square upon h square psi equals to 0. You can call this as equation number 9. If E and V are the total energy and potential energy of the particles respectively, then its kinetic energy, that is half mv square, is given by half mv square equals to E minus V, which gives m square v square equals to 2m E minus V. Substituting this in equation 9, we get, this is our equation 9. We substitute the value of m square v square. We get del square psi plus E pi square m upon h square into E minus V psi equals to 0. You can call this as equation number 10. The above equation is called the Schrodinger time-independent wave equation. The quantity psi is usually referred to as wave function. Which equation are we talking about? We're talking about this equation. Del square psi plus E pi square m upon h square E minus V psi equals to 0. And why do we call this as the independent equation? Why do we call it as the Schrodinger time-independent wave equation? It is only because we do not have t in the whole equation. Okay? That only means it is time independent. The next step is, let us now substitute in equation 10, that is the previous equation, that is the Schrodinger's time independent equation. You substitute h cut equals to h upon 2 pi. You know this in quantum mechanics, h cut equals to h upon 2 pi. You can name this as equation 11. Then the Schrodinger time independent wave equation is usually written as, only substituting the value of h cut, you will obtain del square psi plus 2m upon h cut square E minus V psi equals to 0. You can name this as equation 12. And this is the entire form of the Schrodinger time independent wave equation. Moving further to Schrodinger's equation for a free particle. For a free particle, V equals to 0. Obviously, when it is the free particle, it won't have a velocity. So we substitute V equals to 0. We put V equals to 0 in equation 12. In equation 12, it will become the Schrodinger equation for a free particle, that is del square psi plus 2me upon h cut square psi equals to 0. You can call it as equation number 13. Moving forward to the time-dependent Schrodinger equation. Time-dependent Schrodinger equation may be obtained by eliminating E from equation 12. We have the equation 12 here. This is the time-independent equation, and time-dependent equation can be obtained by eliminating E from here, E out of here. So what will we obtain out of this? To obtain the Schrodinger time-dependent equation, we will have to differentiate equation 3 with respect to time we get. Let us first check what is our equation number 3. Here it is. Sorry for your inconvenience, guys. Here is equation 3. Psi r comma t equals to psi naught r e raised to power minus I omega t. So differentiating equation 3, we will get curl psi upon curl t equals to minus I omega psi naught r e raised to power minus I omega t. But we know the value of omega, that is 2 pi v. So we just substitute the value of omega and we obtain minus I 2 pi v psi naught r e raised to power minus I omega t. Using 3, you can write it as minus 2 pi I v psi r. You can replace this whole term by psi r. We know the value of E. E equals to h mu. That is, V becomes E upon h. So we just substitute the value of V and obtain curl psi upon curl t equals to minus 2 pi I E upon h psi. Or you can write the equation for E psi and it becomes E psi equals to minus h upon 2 pi I curl psi upon curl t equals to, you can write this term as, you can split it in the form of minus I upon I square h upon 2 pi curl psi upon curl t. Now we know that h upon 2 pi can be replaced by h cut. So we write it again in the form of E psi equals to I h cut curl psi upon curl t. Now substituting value of E psi from above equation in 12, we get this is the value of E psi, and our equation number 12 is del square psi plus 2m upon h cut square E minus V psi. We have the value of E psi. So we will now obtain another equation in the form of del square psi plus 2m upon h cut square. Substituting the value of E psi, we'll get I h cut del psi curl psi upon curl t, minus V psi equals to 0, or del square psi equals to, you take this entire term on the other side and obtain minus 2m upon h cut square I h cut curl psi upon curl t minus V psi. That is minus h cut square upon 2m del square psi plus V psi equals to I h cut curl psi upon curl t. You keep this term on the right side, taking everything else to the left, and obtain this equation number 15. Now this equation contains time. As you can see, this equation contains time. Here it is, and is called the time dependent Schrodinger equation. So guys, the easiest way of determining the time dependent equation is if you see a t term in the equation, whereas if you don't see a t in the equation, it can be considered, or it has to be considered as the time independent equation. Alright? Moving on, equation 15 may be written as, let us see equation 15 once again. This is equation 15, a time dependent Schrodinger equation. Equation 15 may be written as minus h cut upon 2 pi del square plus V psi equals to I h cut curl psi upon curl t. You can call this as equation number 16. All we have done is, we've only taken the psi term outside the bracket because it is common for both. You can check it out in the previous previous equation. The operator minus h cut square upon 2m del square plus V is called the Hamiltonian and is represented by h, while operator I h cut curl by curl t operator on psi gives E, while may be seen from 14. Which may be seen from 14. So the whole point of writing the equation 15 in this form is, we get to separate this term I h cut curl psi by curl t term, which can be written as E, and the Hamiltonian that we have is h. Thus equation 16 may be written as h psi equals to E psi, replacing this term by psi, E. So you get h psi equals to E psi. The above forms of the Schrodinger equation describe the motion of a non-relativistic material particle. So guys, this was our entire discussion on the Schrodinger's wave equations. I hope you all enjoyed the video. If you all liked it, give it a thumbs up, share and subscribe. Thank you so much. Take care, stay safe and goodbye. So guys, this was the entire discussion on the Schrodinger's wave equations. I hope you all enjoyed the video. If you all actually liked it, give it a thumbs up, share and subscribe to my channel. Thank you so much for watching. Till then, take care, stay safe and goodbye.